very like you apply for and during the same.
Independent process.
Yeah.
And this one.
But is our
Speaker. Well, it's on which.
but we are not hearing anything.
Oh, hard.
Yeah,
Yeah, he says he can hear us, then it's probably.
Oh, but we can hear you though.
oh, you guys can't hear me, let's see here. Okay, can you hear me now?
Yeah, hello.
Yeah, I'm ready when you guys are.
I have a pen. I think you can use your finger, but
I need to use.
it works pretty well, actually.
This is back to. I can be sentenced.
You see, you see,
Like the recent one.
you just wanted us to.
I don't know how
I couldn't hear you, I couldn't hear you telling them that they're.
Or you cannot hear. Can you hear us talking?
You hear, you guys, I couldn't hear that, you couldn't hear Kurt.
Oh, wait, so you can hear her?
Yes, totally.
Yeah, so it's probably the speaker
Oh,
here.
it's the
Yeah.
probably the output here is.
So, yeah.
Hi, Hart, can you say something?
Yeah, I can hear everybody.
Yeah, okay,
Nice.
now we
Okay,
can
nice.
hear you.
Okay, great.
Okay. Hello, everyone. So we're happy to have Hart here today to tell us about convoluted fermions and the fractional formula of almost Pauli effect. Yeah, let's welcome Hart.
Thanks. Yeah, it's really great to be back virtually. I enjoyed giving one of these seminars during pandemic, and yeah, it's fun to do it again. So today I'm going to be talking about some recent work that I've been really excited by, and connected to experiments that have also been happening at Cornell, among other places. And yeah, I'm going to explain some of our attempts to understand those experiments. So this talk is mainly going to be based on work that I did in collaboration with Liang Fu and his two amazing students, Aiden and Nisharga. Although I also want to acknowledge some collaborators on related work around issues connected to fractional translators and the Quantum anomalous Hall effect. And also I want to mention that around the same time, there was work from the Harvard group, which corroborated many of the things that we were saying. So that's very exciting too. All right. So I don't need to spend a lot of time on justifying why we should study 2D materials to this kind of audience, but just to get everybody on the same page, we have all been very excited in recent years by the development of atomically thin 2D materials like graphene and TMDs. And what really is so amazing and useful about them is just how tunable they are. You can do things like tune their density via gates, put them on different substrates, layer them in all kinds of different ways. And you can also create samples with high purity. And all of this allows us to really try and push toward new kinds of physical regimes that had not been really accessible before. One very prominent example that has been the center of our attention for the past several years is what happens when you take two atomically thin layers and you twist them by a very little bit, of order 1 degree, leading to what we call Moiré superlattice with spacing that's dramatically enhanced, like scales up to 10 nanometers, compared to the actual atomic spacing in the materials themselves. And the consequence of this is that the electronic band structure gets dramatically reconstructed, and correlation effects can be enhanced very significantly compared to just the monolayer situation. And this leads to a whole new plethora of interesting correlated phases that people can engineer at Cornell, among other places, including things like generalized Wigner crystals and charge orders, superconductivity, which kicked off this field, strange metallic phases, and also topological phases, which are going to be the main subject of this talk. And so broadly, what excites me about all of this is that I think these types of systems really can provide a new window into an interplay of Hilbert space topology and strong correlations, and hopefully give us access to even new types of quantum phenomena that we've never seen before in nature. So to just give a little bit of more specificity to that last statement, I can be a theorist and be maximally reductionist and think of all of these systems as essentially just 2D systems of electrons in periodic potential with kinetic energy like this, strongly interacting through, say, long-range Coulomb interactions with interaction strength 1/r, because it's sort of just the basic quantum many-body problem that we all tend to start with our first year of graduate school. But like in our first year of graduate school, we quickly discover that we can't actually diagonalize this Hamiltonian or actually solve anything about it. But nevertheless, it's actually useful to start from this picture, make some basic limiting statements about the types of problems that I'm going to be interested in today. So in particular, I can construct a simple phase diagram in terms of the ratio of the potential or interaction energy to kinetic energy, and ask about different limiting regimes. So we know that, say, for very weak interactions, the electrons are basically free. They propagate like ballistic plane waves with dispersion that is essentially quadratic. Okay, it goes like p squared. And what happens to the electrons in these systems is they just fill up a Fermi C up to some Fermi level. Okay, and this is the basic physics of ordinary metals. On the other hand, in the complete opposite regime, the very strong interactions, the electrons have a much harder time moving. Okay? They become essentially localized, and the energy levels are basically just flat. Okay? And you may think that the sort of simplest consequence of this is that they may want to just form a crystal, electrons being just stuck, say, to the periodic lattice. But if the Hilbert space topology is just right, correlations can actually lead to much more interesting kinds of phenomena. Most classically, the fractional quantum Hall effect. Okay, you can get things like anyons, long-range entanglement, all kinds of crazy things in this regime as well. Okay, but that traditionally has been an area of a limited number of systems, basically 2D systems in a strong perpendicular magnetic field. And the advantage of 2D Moiré materials is really that we can traverse this phase diagram. Okay? And by we, I mean the experimentalists. Okay? Via, for example, either twisting or via tuning an electric field perpendicular to the sample, which we call displacement field. You can basically think of as tuning bandwidth. Okay? And the hope is that somewhere in this region here, we can get access to new types of correlated phases. Okay? And this promise was borne out now almost a year ago by the discovery of what I'll term for this talk the fractional quantum anomalous Hall effect in a twisted transition metal dichalcogenide known as MOT2, molybdenum ditelluride. And so this is basic physics is you have states with fractional Hall conductivity at persisting all the way down to zero magnetic field, which means you need spontaneous time reversal symmetry breaking. And the initial observation of this physics was from Xiaodong Xu's group at the University of Washington. It's basically an optics measurement of compressibility, which I've shown here in the middle. So the x-axis here is going to be density, y-axis is magnetic field, and the colors you can think of as denoting compressibility. So the dark regions here are incompressible states. And I'll point in particular to these two curves right here on the right, which kind of, you can't see one of them very well, but you can see the one on the left fairly well. And you'll see that you have these sort of dark features going all the way to zero magnetic field. Now, what does this have to do with the Hall effect? Well, there's this thing called the strata formula, which relates the slope of these lines to the Hall conductivity. So in particular, the 2/3 and here this other one is located at filling 3/5 case, both have slope 2/3 and 3/5, which suggests a fractional Hall conductivity. And then shortly thereafter, a experiment came from the Cornell group. It's probably known very well to some of you, also corroborating at least the 2/3 case. Right? And when I first saw all of this, I was thrilled, okay, because again, this really had only been the realm of 2D electron systems in magnetic field. Now we have access to a completely new type of phase diagram at zero magnetic field, right? But we needed transport, and that remarkably came out quite quickly after the initial measurement. So basically, I'll start with the figure in the middle here. So this is, again, all these figures are from the Washington group, where if I sweep filling and measure resistivity, so blue curve is going to be Hall resistivity, red curve is longitudinal resistivity, you see reasonably quantized features at filling 2/3 and 3/5 again. And you may think, well, this quantization doesn't look that great as you tune filling. By the way, all this is at zero magnetic field again. But if you tune displacement field, you see very nice quantization, okay? Sorry, magnetic field, you see very nice quantization. And you also see hysteresis, which signals the spontaneous breaking of high universal symmetry in the form of ferromagnetism, right? And moreover, using displacement field, you can navigate a whole phase diagram here, tuning bandwidth in addition to filling, and go from quantum Hall states to more resistive types of phases, which I'll talk about towards the end of the talk. Okay. And then, as if all of this wasn't enough, completely different system, the same phenomenon was discovered, namely in rhombahedral pentalayer graphene on hexagonal boron nitrides. I would never have expected any of this physics to happen there. I think most of us wouldn't have expected this, but here we are. And really amazingly, they see even more fractions. This is from Longju's group at MIT, and then actually even more features in the RXX measurement. So you see plateaus with, say, not only 2/3 and 3/5, but 2/5 and 3/7, 4/9, 4/7, along with corresponding resistivity dips, which is what you would expect in the ordinary quantum Hall effect. And also the phase diagram that they see tuning displacement field is very similar. All right, and then as if that wasn't enough, very recent measurements at higher filling, also from the Cornell group, have seen evidence of a fractional quantum spin Hall state near nu equals 3. This is a different twist angle. So the earlier twist angle was quite a bit higher. This is at 2.1 degrees. And we don't really know what the physics of this state is at this point. But I think I have been thinking a lot about this recently. Many of my colleagues have been thinking a lot about this, and hopefully there will be some progress in understanding what exactly is going on here. This is very exciting as well. All right. So just to kind of go back to broader philosophy here. So why is any of this really all that surprising? Well, if we're being especially naive and maybe not as open-minded, maybe we would have expected that at zero magnetic field, strong lattice effects and correlation effects would tend to want to pin electrons to the lattice and form a Wigner crystal, like what I talked about before. And in particular, this order is still around, and we need, many folks have been trying to understand the interplay of Wigner crystallization with quantum Hall recently, in a saga of papers, particularly related to the pentalayer graphene example. I won't really touch on this in this talk, but this is an ongoing effort to really nail down the energetics here. But instead, I'm going to ask a somewhat higher level question of simply what is the right choice of degrees of freedom for talking about fractional quantum anomalous Hall, and what choice of degrees of freedom is this really natural physics, right? And the answer I'm going to propose is one that's very familiar from quantum Hall, which is the framework of composite fermions. And what I will try to argue to you in this talk is that composite fermions really explain fractional quantum anomalous Hall physics very naturally, and hopefully also, I think, fractional quantum spin Hall. And one central feature of all of this is a really exotic, interesting kind of non-Fermi liquid phase near half filling, which I'm going to term the anomalous composite Fermi liquid. And I've been over the moon about this since our work came out, because it's really rare for any theorist to actually explain anything about experiments. But I think there's already good evidence that this anomalous composite Fermi liquid is there. All right. So just to give a broader roadmap for this talk, and by the way, anybody's free to interrupt me at any time with questions. I'm going to start with a lightning overview of quantum Hall and composite fermions in case there's some folks who aren't as familiar with this story. Then I'm going to talk about the microscopics of twisted MOT2. I'm mainly going to focus on the system. I'm not going to talk as much about pentaslayer graphene. And I'm going to also then motivate in the system why there's this anomalous composite Fermi liquid, why composite fermions are important more broadly, and do so via numerics. So this is exact diagonalization evidence here. Then I'm going to talk about some broader theory foundation, develop an effective field theory for composite fermions and Chern bands, move on to some observable consequences, and then sort of give a broad overview of what I think is most exciting in this field, which has really exploded the past several months. All right, so just to give a broad review of quantum Hall, the traditional quantum Hall effect, I start with a 2D system of electrons in a strong perpendicular magnetic field. These guys will want to undergo semi-classical cyclotron orbits and form quantum mechanically, very perfectly flat, highly degenerate Landau levels with spacing given by the cyclotron frequency. And the usual integer quantum Hall effect, so where the Hall conductivity is quantized in integers, just comes from filling these Landau levels completely with electrons. Okay? You get these nice incompressible states with quantized, here we have Hall resistivity and vanishing longitudinal resistivity. Okay? And if we turn on interactions in these systems, you get a whole new zoo of amazing phases. So here I just included the Coulomb interaction. And these phases have fractionally quantized Hall conductivity. So you see all these features at 2/3 and 2/5 and 1/3 and so on. And again, characterized by vanishing of the longitudinal resistivity and quantization of the Hall resistivity. And one kind of really amazing consequence of all of this is that, as we've come to know, the low energy excitations in these systems are what we call anyons, which have fractional charge in statistics, right? Which kind of leads to another philosophical statement. Really, since the discovery of quantum Hall and the sort of sophisticated understanding that we've had since then, one major goal has been to look for this kind of fractionalization behavior in other systems. And really, despite a great deal of effort in many contexts, including high TC, heavy fermions, magnets, and also Moiré, there really has not been any smoking gun discovery until this fractional quantum anomalous Hall effect. And that's another reason to really take it seriously and view it as exciting. So anyway, now, how does one actually understand, in a modern way, the existence of fractional quantum Hall phases, and how does one map the usual quantum Hall phase diagram? All right, so the framework to do this is what we know as flux attachment. So you take your original system of electrons in magnetic field and adiabatically attach some flux, which I'm drawing as a solenoid here. And for each flux quantum, you can think of the electron statistics as being shifted by pi. Okay, just coming from the Aharonov-Bohm phase, when I take one electron around another, or sorry, one now composite particle around another. And in particular, if I attach an even number of flux quanta, I will get what we know as composite fermions. I just shift my electrons statistics by 2 pi. Whereas if it's an odd number, this is what we call composite bosons. And another consequence of this is that when I do this flux attachment, the field experienced by the composite particles is reduced by some amount proportional to the density. Okay, that's just the number of fluxes that you attach. Right? And one additional consequence is that these composite particles actually, they're not completely like ordinary electrons. Okay, they couple to now a new emergent fluctuating gauge field with Chern-Simons term. Okay, rest assured, I could write this in a properly quantized way, but for the purposes of this talk, I'll use improperly quantized Chern-Simons terms. All right, so the composite fermion framework can be used to explain the observed fractional quantum Hall states in nature. So if I attach 2 fluxes to each electron, for example, now my composite fermions are going to be experiencing a screened magnetic field. And I'm going to tune the density so that they fill an integer number of Landau levels. Then these guys are going to form an integer quantum Hall state, an incompressible state. So what are the electrons doing in this situation? Well, you can compute the corresponding filling of the electrons and their Landau levels. And you see that actually it's a fraction. And that fraction lies along what we call the Jane sequence. And really remarkably, the Jane sequence really maps on to the vast majority of observed fractional quantum Hall states in nature, right? And also, I think really amazingly as well, the composite fermion framework really does explain broader aspects of the quantum Hall phase diagram as well. In particular, the presence of what we call the composite Fermi liquid. So if I take the number of Landau levels that the composite fermions feel to infinity, then the amount of magnetic, so then the filling fraction is going to approach 1/2, and the amount of magnetic field that they feel is going to vanish, all right? And as a result, okay, what do fermionic degrees of freedom do if they don't feel a magnetic field? They're going to form a Fermi C with Lagrangian roughly written by this. So in particular, the composite fermions are still coupled to this emergent gauge field, which means that actually it's a very strongly interacting system and is a non-Fermi liquid. But also something I want to emphasize is that as I dope this state, I get the Jane sequence. So you can think about this really as a parent of fractional quantum Hall states. And it's very physical. This metallic state is observed regularly in quantum Hall systems, and you can see it in this picture as this region of finite longitudinal resistance and linearly varying Hall resistivity that's actually order 1. Okay, so it's different from like an ordinary Fermi liquid in that way. All right, so then we can ask the question of if the composite Fermi liquid is the parent of ordinary fractional quantum Hall, is an anomalous composite Fermi liquid the parent of fractional quantum anomalous Hall? And to answer this question, we'll start with the microscopic physics of twisted MOT2, apply numerical techniques, and build a theory foundation from there. All right, so now I'm going to actually get into the twisted TMD physics. So in particular, I'm going to broadly ask how one can think about obtaining fractional quantum Hall at zero magnetic field. What are the essential ingredients for this? Well, the first thing, which I already mentioned at the beginning of the talk, is spontaneous breaking of time reversal symmetry. In other words, through for example, through ferromagnetism or other means. And this enables then the electrons to be able to see what I'll call a pseudo-magnetic field, which I'll sort of cartoonishly write like this. And the next ingredient is that the system needs narrow Chern bands that look roughly like Landau levels. So the kinetic energy is much smaller than the potential energy. They're very flat. And one needs the Hamiltonian projected into these Chern bands to resemble the lowest Landau level under some definition of resemble, which theorists are still really trying to work out in detail. But that will not really be the subject of this talk. And importantly, TMD materials are actually really good candidates for realizing these two ingredients. So at least in the first one, because of the strong spin orbit coupling in TMDs, the spin valley locking, which leads to Ising ferromagnetism. Okay, so these are quite good magnets. And yeah, as you see here, this is a sort of schematic plot of the Brillouin zone. You can see different valleys alternating between up and down spin. And when we twist these materials, it is possible to access a flat band regime with Chern number c equals 1. And you can think about sort of the origin of this physics as coming from a Skyrmion lattice in pseudospin space. I'll sort of explain what this means on the next slide. But in particular, this pseudomagnetic field that the electrons feel can be written as a winding number for a layer pseudospin. Okay, so this is importantly, this is not the thing that gives you the magnetism. Okay, this is a different pseudospin object from the actual electron spin. All right. So now a little more detail. We'll focus on a continuum model of a twisted MOT2 HOMO bilayer. And we're mainly going to focus on twist angle 2 degrees. And the continuum model here is written like this. So importantly, these T's are interlayer tunneling. V's are the intralayer Moiré potential. And again, this is projected into a single valley. Right? And these parameters, V and T, are going to be fit to DFT. Right? Now, importantly, I mentioned the pseudomagnetic field on the previous slide. This model can actually be mapped via unitary transformation to precisely a theory of electrons in this kind of pseudomagnetic field, seeing a vector potential which has this non-trivial winding behavior. And again, this is in the layer space, so this comes from a layer pseudospin. All right, and the consequence of this is that the single particle spectrum is going to contain a narrow Chern band with Chern number -1, okay, shown here. All right, and this is for the one valley. Now, how are we going to attack studying the physics of this system? So we're going to project into this narrow band, but importantly, we're not going to assume ferromagnetism. So we're going to keep spin in the game, and we're going to introduce Coulomb interaction. So all of this is non-interacting band structure, very important. So one of the nice things about the TMDs compared to the graphene case is that you get the flat band without having to introduce any complexity from interaction. So we don't have to do things like Hartree-Fock. And so when you add interactions, you get a final microscopic Hamiltonian that looks like this, where the second term here is the projected Coulomb interaction. So all the information about the band structure is coming from these U's, okay, which are the Coulomb matrix elements. And these epsilons are just the single particle dispersion. Sigma is going to run over the spin or equivalently valley index. And the only thing in this whole Hamiltonian, which depends sensitively on band topology, is going to be these matrix elements U. And I'm going to study this Hamiltonian in exact diagonalization and try to look for evidence of an anomalous composite Fermi liquid at half filling and go from there. All right, so this is what the actual ED data looks like. So I'll step through this pretty slowly. The left panel here, left two panels, are plotting the energy spectrum on the y-axis versus many-body momentum. The top here corresponds to an ordinary Landau level on a torus. the bottom here corresponds to the twisted MOT2 case, and I'll explain these tiles on the right here. We can think of these as essentially plotting the Brillouin zone for right now. And you see that for the Landau level case, you get some pattern of ground states here that match up perfectly to the pattern of ground states that are seen for twisted MOT2, although the excited states differ by a little bit. And also the colors here down here denote spin. So you see this is spin polarized. All these dots are red. If I take these Brillouin zone plots here and I tile them with the locations of these states in K-space, well, you get something that looks kind of like a Fermi sea. Okay, this isn't a smoking gun. This isn't. I'm not actually measuring the spectral function or anything, but you can see the shape of a Fermi surface. Now, if we go to larger twist angles, what happens? So ignore this top right plot here for a minute. This lower right-hand plot is at 4.5 degrees, and you see a rather different pattern of ground states. Now, if I look at the overlap between these ground states and block states, okay, so that's actually what the colors on the right of these right-hand Brillouin zone plots denote. You see that where these guys live is in the band minima, okay, at the edge of the Brillouin zone, and they have very good overlap with electronic block states. So this is an ordinary metal of electrons. Over here, what this green color tells you is that actually these this ground state family here doesn't have good overlap at all with the electronic block state. So the degrees of freedom are something else, i.e. composite fermions. Okay. And all of this is consistent with similar numerics that was done by the Harvard group using different DFT parameters. So actually that gives good evidence that all of this physics is pretty robust to the details of the band structure coming from DFT. All right. Before I move on, are there any questions about sort of understanding this data? Okay. So now I'm going to give a little bit of theory foundation for all of this. So why expect any of this physics? So I'm going to claim that the basic intuition of flux attachment is still relatively applicable to fractional Hom anomalous Hall systems. Okay, and we can see this in a few ways. One is just to try and do naive flux attachment, screening this pseudomagnetic field that I mentioned. All right, and this gives essentially the correct long wavelength physics, but really if you want to do this exactly properly, you should do lattice flux attachment. You should incorporate the Berry curvature in a more natural way. But that's really tricky. Lattice Chern-Simons theories, if anybody's ever worked with them, are very, very cumbersome to actually work with in practice. Another option is to project into the band and actually work out a detailed composite particle theory doing what's called vortex attachment on the non-commutative space of the Chern band. This is similar to the topic I spoke about last time I gave one of these seminars. And this is a really important open problem in the field, but it's very, very hard. So I won't do this either. Instead, because I spent time in Cambridge, I'm going to do partons. And the advantage to the parton procedure here is that it naturally incorporates the physics of the Moiré superlattice potential, and it has a very broad applicability to studying things like quantum phase transitions, okay, out of the quantum Hall state. And so I'm going to mainly use this technique for this talk. All right, so what is the actual parton decomposition? So we're going to take the original system of, the original electronic variables and split them into a bosonic parton, which we'll call phi, and a fermionic parton, which will ultimately be our composite fermion, called psi. Okay, and this procedure of splitting these guys has a gauge redundancy, so there's going to be an emergent U1 gauge field floating around. under which C is neutral, but phi is going to have negative charge and psi is going to have positive charge. And I'm going to put the charge of the actual electron, so the physical electromagnetic charge, on phi. All right. So I'm also going to include the Moiré superlattice potential in the definition of big A mu, the electromagnetic gauge field. Okay, so phi sees it, and it sees the same band structure as the physical electrons. So that means it's filling return one band by half. Okay, but the behavior of bosons in half filling of a flat band is rather different from that of fermions, and their tendency will be to form an incompressible ordinary quantum Hall state with Hall conductivity 1/2. So this is what we call a bosonic Laughlin state. And if we take this incompressible gap state of these bosons, integrate out the bosons, what we'll be left with is a theory of, again, a composite Fermi C, composite fermions coupled to this fluctuating gauge field, plus the Moiré potential. Okay, and importantly, all of this at zero background magnetic field. Okay, there was never a magnetic field introduced in this discussion, and in particular, if I take the density and I dope it a little bit, so I change the filling away from nu equals 1/2, the composite fermions will start to feel a magnetic field, just like in the ordinary flux attachment case. Okay. So I'll just show the final action for all of this. It's very similar to the usual Halpern-Lee-Reed action for the composite Fermi liquid. So the only main differences I'll highlight are in this first term here. So the Moiré superlattice potential is being included as a scalar potential, which varies with the same period as the Moiré lattice. And also there's this last term here, okay, which is not in the usual composite Fermi liquid theory, which couples the time component of the fluctuating gauge field of A mu to this background density, which determines the where 1/2 filling sits. Right. So in particular, if I integrate over AT, you get a constraint that the magnetic field felt by the composite fermions, like I quoted on the last side, is proportional to the doping away from half filling. And also importantly, at half filling, again, composite fermions don't feel any magnetic field and will form a anomalous composite Fermi liquid metal. Okay. Now, if we had done more traditional flux attachment using this pseudomagnetic field, it would be natural to interpret this rho bar here that I mentioned a couple seconds ago as the curl, at least the uniform part of the curl of the pseudomagnetic field. Okay. I'm not including additional contributions. So this is all, this is all long wavelength effective field theory. All right. So what are some of the consequences of the anomalous composite Fermi liquid? Well, the first one is that you get a similar Jane sequence of fractional quantum anomalous Hall states, which are already consistent with experiment, just by tuning charge density, okay, no magnetic field. And the basic algebra of this is very similar to the usual quantum Hall case. Dope a little bit away from half filling, fill an integer number of Landau levels. This gives you a relationship between the electronic density and the density of 1/2 written here. Oh, by the way, even though the original underlying electrons are in a Chern band, when I dope from 1/2, because the composite fermions here feel a magnetic field, it should still interpret the energy levels of the composite fermions as Landau levels. So that's why I'm using the word Landau levels here. And if I just rewrite this expression in terms of fillings, so I just multiply each side by the Moiré unit cell area, you just get the usual chain sequence. Okay, and so that naturally then usual quantum Hall is any evidence. This leads us to think then that the most prominent fractional quantum anomalous Hall states in experiments will lie along this sequence. And not only is this borne out in experiment, both in the pentalayer graphene case, but also in MOTE2, but also it's borne out in our numerics. So for example, we can look at Jane filling fractions. Here I've shown the 2/3 and 3/5 case. Again, this is at twist angle 2 degrees. And you see the expected topological degeneracy of the ground states here. Sorry, is there a question? Okay. I'll keep going. So all this is great, but what are some more smoking gun types of observable signatures, and what's already been seen in experiments so far? So the first thing that should be noticed about the composite Fermi liquid, which I already highlighted several slides ago, is that it is a metallic regime, but it's one with a very large order 1 Hall effect, right? And that's actually already been seen, although I didn't highlight it in the transport experiments I quoted at the beginning of the talk. So if you look near half filling, you see this large Hall effect here. This is for the MOT2 case. The longitudinal resistance doesn't look quite as good here. It's kind of featureless, but you can definitely see in the pentalayer graphene example a nice metallic region near half filling and this order 1 Hall effect. All right, and in particular, if I want some more sharp smoking gun evidence for a composite Fermi surface, one needs to go beyond this and look toward something like quantum oscillations, which is actually where most of the evidence for a composite Fermi surface in ordinary quantum Hall comes from. So I'll start by talking about that ordinary quantum Hall case. So if I dope away from half filling, we already have said several times, the composite fermions will undergo cyclotron orbits, and this will cause oscillations in the magnetoresistance. In particular, if I, not I, the experimentalist, stick on a externally applied periodic electrostatic potential, there will be resistivity minima when these cyclotron orbits are commensurate with the externally applied potential. Okay? And so this is seen very beautifully, for example, in this recent, now I guess this is 10-year-old, but still really beautiful data from Shayagan's group. And the locations of these minima are really in kind of amazing agreement with composite fermion mean field theory. Okay? It's really striking, given especially the non-Fermi liquid nature of this system, that the expectations match on as well as they do. All right, so what about the Moiré case? So there's this cool feature of the anomalous composite Fermi liquid example that the Moiré potential kind of comes along for the ride in the composite Fermi liquid theory. So that means that there's already a built-in periodic potential. And that means, in particular, that there will be no need potentially for an externally applied potential. You would just have commensurability oscillations, tuning doping alone without any externally applied periodic potential. And so we call this intrinsic commensurability oscillations. And yeah, as mentioned before, we dope away from 1/2, you undergo cyclotron orbits. So here's a kind of schematic picture. And when the cyclotron orbits are commensurate with the periodic superlattice, sort of again schematically drawn here, you get resistivity minima, right? At least the actual formula for the locations of these resistivity minima is shown here, and the actual period. So the minima are periodic in 1 over the doping, and actually that period is pretty reasonable. It's about 2.3 we estimated. Okay, so these samples, though, they're much too dirty to actually see this physics now, but hopefully in the future, as sample quality improves, we can actually see these kinds of quantum oscillation effects. All right, and so what have the experiments actually observed? Just to summarize, so we see these metallic regions with large Hall effect. And we also see quantum anomalous Hall fractions that are all consistent with Jane's. That's pretty good evidence that they should converge on a composite Fermi liquid. But what's not yet seen are these commensurability oscillations, as I just said, or some more smoking gun signature of the composite Fermi surface. Okay, so just to summarize the talk so far, we discussed the discovery of fractional quantum anomalous Hall and twisted MOD2 and pentalayer graphene. And hopefully I've convinced you that composite fermions explain the observed phases and provide a launching point for studying the phase diagram of the system. I'll get to that in a moment in more detail. But in particular, I want to sort of insist that the linchpin of the quantum anomalous Hall phase diagram is the anomalous composite Fermi liquid. And it's exciting that there already seems to be experimental evidence for this. So now I'm going to talk about some broader vision for where we go with all of this. So as I kind of mentioned broadly at the beginning of the talk, what excites me about all of these systems is just how much the phase diagram of fractional quantum anomalous Hall is enriched compared to ordinary quantum Hall. And in particular, ordinary quantum Hall systems, we can understand the phase diagram in more or less this way using this cartoon picture from before I was born. And you can sort of map different quantum Hall phases in terms of filling, which can be characterized by the Hall resistance, and disorder, which can be loosely understood as the longitudinal resistance. All right, and so you get these different regions of plateaus. So here's, say, n equals 1 integer quantum Hall state, here's 1/3, and you get these cascading fractional quantum Hall states below. These crosshatched regions here correspond to composite Fermi liquids. Right, and that's the basic picture of the phase diagram. Many things are still not understood about it, in particular, the behavior of the critical exponents at different quantum Hall plateau transitions is still very poorly understood, and also yet to be explained is the universal values of the resistivity, and they're measured at these transitions as well. But we'll go beyond these kind of old hard questions and just mention what is really exciting about the zero field case. Okay, so what's exciting is instead of just having this kind of old phase diagram, you have new kinds of competing phases that are possible at zero field. That are disliked by the presence of an external magnetic field. So examples include metals and charge order states and superconductivity. And also we get a new axis on the phase diagram in the form of displacement field bandwidth. Okay, so sort of in very general terms, all of these quantum Hall states that we're getting, we can think about how they would evolve at very, very large displacement field to an ordinary metal. Right? And we don't really know at this point what the details of the phase diagram in between is. Okay, and hopefully that leads to exotic new kinds of quantum phase transitions. But now that we sort of have this baseline using composite fermions for doing theory, hopefully some of this can be elucidated both by an interplay of theory and experiment. Right. So one thing in particular that really jumps out at me about the experiments and that I'm really excited and kind of vexed by are particular types of quantum phase transitions that are seen, or at least, okay, we don't know that they're direct transitions yet, but I'm hopeful between quantum Hall states and ordinary metals. All right, so this is in addition to other quantum phase transitions that have been seen that are at least somewhat reasonably well understood between, say, composite Fermi liquid and Fermi liquid, tuning displacement field. I already showed some evidence for that in the ED. But what is really exciting to me is the case where, say, I start with the 2/3 state, I change displacement field, and then, not me, the experimentalist, change displacement field, and go into a more, an ordinary kind of resistive regime, which may be metallic. Okay, and this is a line out from the Xiaodong Xu experiment. You see these big peaks here in the longitudinal resistance. Okay, that tells you that there's some order 1 in units of h over e squared value of the resistance as you go from this quantum Hall state to a more resistive state. And that's really, having an order h over e squared resistivity, that's a big sign that you may have a continuous quantum phase transition here. But in this case, as opposed to, say, going from composite Fermi liquid to ordinary Fermi liquid, there's really no theory baseline. Okay? We don't have any idea how to do this kind of interpolation. And that's, I think, really exciting to me that this problem exists and hopefully we can solve it. So yeah, and hopefully composite fermions will provide a starting point for finding answers. And I think we've already made a little bit of progress actually on this, but it's still a massively hard problem. So yeah, with that, I will wrap up and take questions. Wait, I can't hear anybody.
Any questions?
Oh, okay.
Yeah.
Do you expect a quasi-particle in these fractional quantum anomalous Hall regimes to have an associated magnetic moment, like a superconducting vortex? Not in like in real magnetic.
You mean like by quasi-particle? You mean like anyons or like? What do you?
Sure.
Yeah, so that's a really interesting question. I think. Okay, I'll kind of broadly answer it by saying I'm not completely sure. I think this depends on some of the details of the particular, what we call symmetry-enriched topological order you get, and nobody has actually classified which, detailed fractional quantum anomalous Hall states you can get at each filling fraction yet. This is something I've been thinking about, and I think actually like using some of these parton ideas from earlier, you can constrain the types of phases that you can get. But for example, like, in a stage where you have, say I'll do momentum, rotational symmetry fractionalization. So you will have anyons which carry a quantum number under spatial rotation. So they transform. You think about them as having a fractional angular momentum. Okay, so that would be really interesting, but we don't know if those states are here.
So the composite Fermi liquid. So people are very interested in doing these interferometry experiments in these fractional quantum Hall and fractional quantum anomalous Hall states. Is there like an associated little Parkes effect or something for the composite Fermi liquid that you could probe?
I don't know that that is an active area of research. I will hopefully be able to give you an answer soon. But yeah, I don't have that's a very good question. I want to know the answer to.
So the parton theory right now is still at the mean field level, or have you incorporated the fluctuations of gauge field?
So I don't think that there's any actual particle hole symmetry here. I mean, microscopically, the particle hole symmetry is broken by the dispersion of the band, so essentially the kinetic energy. So I don't see a really clear reason why you need to have particle hole symmetry. Certainly in the clean limit, you wouldn't have it. There's this question that also arises in ordinary quantum Hall of whether disorder can lead to an emergent particle hole symmetry, and maybe some emergent, physics that loosely corresponds to the direct composite fermion of some. I don't know whether that works out here, but in any case, yeah, I think for what we should expect for a clean one of these systems projected into Chern band at half filling, we shouldn't expect any kind of particle hole symmetry to hold.
Yeah, and do you have any comment about if you do not do this kind of composite fermion Fermi surface, but you do like a SONS, you do flash attachment to a Dirac fermion? to
Well, because of the absence of particle hole, the
Okay,
direct composite fermion is not really. I don't think it's super relevant.
I see, I see.
Yeah, again, it may be relevant with disorder. I don't know, but there's also a question in quantum Hall too of like, the arguments for particle hole symmetry with disorder. Do you really get the direct composite fermion, or you just get like a state which mimics the transport of the direct composite fermion? These are questions that folks have not managed to sort out for quite a long time. Or well, I guess now 9 years or so that the direct composite fermion's been around.
Maybe a slightly different way to ask the same question as well. Okay, particle symmetry is broken, but we do know that the anti-CFL is somewhat different from CFL, right? Even in the Landau level setting. So which one would win? I don't have to.
Yeah, I don't know. That's so certainly what we've done so far does not differentiate between the anti-CFL and the CFL. It would be interesting to think about experimentally what could distinguish. There probably is something. Well, you'd have to have very high resolution for quantum oscillations to probably tell the difference, but that would be my go-to starting point. I think there are, I think, in calculations that people have done, like small differences between the Dirac and ordinary CFL and anti-CFL cases in quantum oscillations, but like Mike Mulligan has done these kinds of calculations. But also, I don't think those agree with the most high resolution experiments in gallium arsenide either. So yeah, it would be interesting to try and find some better way of differentiating. But yeah, I agree with you. There's no, I could have picked the anti-CFL here and the story would have been the same.
Okay, if there are no other questions, it's hard to get.
Yeah, thank you for having me.
Thanks, Howard. Very nice.
Thanks.